So we're going to pick up on section 1.2 right here with increasing, decreasing, and constant function on an interval. A function f is increasing on an interval if for any 2 points in the interval a positive change in x results as a positive change in f of x. And so what this means is that if something is increasing, as x is getting bigger, y is also getting bigger, and so that would be an increasing part of a function. And that line right there is simply an increasing function because it's always increasing. If a function is decreasing, we would say that as x is getting larger or increasing, y is getting smaller or decreasing. So that line there has a negative slope and it's a decreasing function. And a constant is as x is getting larger, if y stays exactly the same, then that's considered constant. It's neither increasing nor decreasing. So analyze a function for increasing and decreasing behavior. Now we have f of x equals the absolute value of x plus 3 minus the absolute value of x minus 2. Now they've been nice enough to break this into a piecewise function for you so that you don't have to worry about that. But we have that f of x equals negative 5, where x is less than or equal to negative 3. So that's going to be at negative 5 until we hit negative 3. So we're going to put a closed dot there. So that's the first piece of this function. So now I want to get a little different color. Apparently it's only going to let me have black. We're going to do this piece of our piecewise function. And so this tells us that it's going to be the line f of x equals 2x plus 1. So a line that intercepts the y-axis at 1 that has a slope of 2, and it's going to do that between negative 3 and all the way up to positive 2. So that piece of the line is going to look like that. Pretend that looks good. And then the final piece of this function is going to be that f of x equals 5 if x is greater than or equal to 2. And so identify the intervals on which f of x is increasing, decreasing, and constant. Well, I have two intervals where it's constant, and that's right here and right here. So we would say it's constant from negative infinity to negative 3. And we would also say that it's constant from where x is 2 all the way to infinity. Now the only other piece of this graph is right here. And as x is getting bigger, y is getting bigger, and so we would say it's increasing on the interval where x is between greater than or equal to negative 3 and less than or equal to 2. So lower bound, upper bound, and bounded. A lower bound occurs, so I'm not going to read these definitions to you, but this first one, if something is bounded below, would be something like this type of function, because we see that the y values actually stop at a certain point. This would be the lowest point. There's nothing where y is going to negative infinity, so this function would be bounded below. A function is bounded above, in this case, for instance, because we have a definite maximum value for our y, and there's nothing where y is going to infinity above. A function is bounded if it's bounded both above and below. So let's say instead of arrows, we just have an endpoint. We have a function that goes like this. Maybe it looks like a period of a sine function. And in this case, there's nothing that's going on to infinity in either direction, so we'd say this one is simply bounded, meaning that it's bounded above and below. Boundedness is determined by the range or the y values in the function. Local and absolute extrema. A local maximum of a function is a value f of c that's greater than or equal to all range values of f on some open interval containing c. So if we want to talk about a local maximum, let's just say I go with this function that looks something like this. So if we're talking about a local maximum, right here we have part of our function that on an interval actually reaches a higher point and then it starts decreasing again. That would be a local maximum. Whereas if we had a function like this, we'd say it has a local maximum here and it has an absolute maximum here, because that is the highest that our y value goes in this function. A local minimum, similarly, we can have a function like this, where there's not an absolute minimum because y goes to negative infinity, but there is a local minimum right there. And an absolute minimum would look something like this. Here we have a local minimum. Here we have an absolute minimum because that is the lowest value that our y value reaches. So local extrema are also called relative extrema. Identifying local extrema, we have the equation x to the fourth minus 7x squared plus 6x. Well, I am going to go to my graphing calculator, and we're going to learn some things right now. I'm going to clear out my memory because I have a lot in here right now. And so I'm going to reset it. I'm going to reset all RAM. Reset. They really want you to be sure you want to do this. And so the function that we want to put in is x to the fourth minus 7x squared plus 6x. So I'm going to go to y equals, and I'm going to put in x to the fourth, and I need to arrow out of those. Okay, for some reason my memory is not holding. So minus 7x squared plus 6x. Minus 7x squared plus 6x. And let's go ahead and graph this and see if our window is working. My calculator is set to the default window right now. Okay, and it's not quite working because I'm not seeing my absolute minimum in this problem. So I need to increase, or decrease rather, my y minimum. And I'm going to give it some leeway here. So I'm going to scroll down to the y minimum because that's really what I want to show. And I'm going to go ahead and put it at negative 50 because I think that'll definitely get it on this graph. Okay, now let me look at what the problem is asking, because it said find each local maximum value or minimum value and the value at which each occurs. So if I look at this problem, we have three values that we're going to be looking at. We're going to be looking at an absolute minimum right here. We're going to be looking at a local maximum right here, and we're going to be looking at a local minimum right here. Now what we're going to do is we're going to go to calculate. So I'm going to hit second, and calculate is right above trace. And I'm going to go down to, the first thing I'm going to do is figure out my absolute minimum. So I want to scroll over there, and if you look at the bottom of the screen, right now it's asking for the left bound. So what that means is that we want to go just ever so slightly to the left of the minimum point we're trying to get. We're going to hit enter. And then it says you want to know the right bound. So this is the interval we're looking at. We want to get to the left of our minimum, we want to get to the right of our minimum, and hit enter. And it says, well, there's your guess. Well, I'm just going to hit enter a third time, and it's now going to tell me that the minimum is at negative 2.06 if I round it to the hundredths place, where y is negative 24.06. So this would be our absolute minimum for this function. So now we have a local min that we're also trying to find, and we have a local maximum that we're also trying to find. So let's go back to our handy dandy calculator, And we're going to calculate again. So hit second, calculate, and we're going to we'll do our local maximum this time. So I'm going to select 4. Now it's asking for the left bound, so I need to arrow over. We're going to trace it until we get to where we're just to the left. Okay, that looks good. And then it's asking for the right bound, so we're going to scroll over until we're to the right of that local maximum. And then we're going to hit enter again. And it's going to spit out at us that this maximum is at positive 0.46 and positive 1.32. Now our local minimum, so this is the last one we need to do, so we're going to go to second, calculate. We're going to do another minimum. At the minimum, and it says left bound, so right there is good. We'll hit enter. Let's go to the right of it, and we'll hit enter and enter again, and it tells us that that minimum is at 1.60 and the maximum is at 1.77. So that's how you can use your calculators to find those extrema points. Symmetry with respect to the y-axis. So when we've talked about this is considered to be an even function. And so if we look at f of x equals x squared, if we want to know if this is going to be symmetric to the y-axis, we're going to plug in f of negative x. And when we do that, we get that it is negative x squared, which is x squared. Well, if we look at what we started with, we have exactly the same thing. So when we plug in the opposite of x, if we end up with the exact same function in which we started, we're going to say that this is an even function. And when we have an even function, that means it's going to be symmetrical over the y-axis. If we fold it, it's symmetrical over the y-axis. Likewise, if you see a graph that's symmetric over the y-axis, that you could fold over and it would match up, you can say, I know that function is an even function. Symmetry with respect to the x-axis. An example of this is x equals y squared. So graphs with this kind of symmetry are not functions, except the zero function, but we can say that x negative y is on the graph whenever xy is on the graph. Symmetry with respect to the origin. Now this is the other big one you need to know. If we plug in again f of negative x into our function, so that equals negative x cubed, well, when we work that out and simplify it, we get that this is negative x cubed. And now we compare it to what we started with, and we have that they are exact opposite. So when they're exact opposite, this has symmetry with respect to the origin, meaning if we rotated that graph 180 degrees, it would line up onto itself. Now this is called an odd function. You'll notice with odd functions, look at what the exponent has, and with even functions, look at our exponents. They're even. Checking functions for symmetry. Tell whether the following function is odd, even, or neither. So we're going to go ahead and plug in f of negative x, and we're going to get that this is negative x squared plus 3. And when we simplify that, we get f of negative x equals x squared plus 3. So we look back and we say, well, my golly gosh, that is exactly what I started with. So this is an even function. Horizontal and vertical asymptotes. So the line y equals b is a horizontal asymptote of the graph of a function y equals f of x. If f of x approaches a limit b as x approaches positive infinity or negative infinity. And in limit notation, we look at the limit as x approaches infinity of f of x, and it equals whatever that value is approaching, and it has to be a definite value. Likewise for vertical asymptotes, we're going to look at it, the x equals a as a vertical asymptote of the graph of the function y equals f of x. if f of x approaches the limit of positive infinity or negative infinity as x approaches a from either direction. So let's look at some asymptotes. Identify the asymptotes of the graph. Well, we're basically looking at where is this function impossible. And if we factor our denominator, we get x minus 2 times x plus 1. And it's a big no-no to have a 0 in the denominator. So we would say x cannot equal 2 and x cannot equal negative 1. And what that means is that we're going to have vertical asymptotes where x equals 2 and where x equals negative 1. And these are like electric fences. This graph will never touch those asymptotes. And just to prove it, let's look at our graphing calculator. So we're going to plug in, I'm going to clear out my y equals. And we're going to do x divided by x squared minus x minus 2. So x divided by parentheses x squared minus x minus 2. Why can I not find my other parenthesis? Nope, don't want that bracket. Struggling. And let's graph it. So what we see, this would represent the vertical line where x equals negative 1. This right here would represent the vertical line where x equals 2. And we'll notice this graph never touches it. We can get a better idea if we change the window to negative 10 to 10 and just negative 10 to 10. And you get a better idea of what this graph looks like. And this function also has a horizontal asymptote where y equals 0. And let's look at why that is. Can y ever equal 0 in this case? And no, it can't, because in order for y to equal 0, your denominator would, I take that back. I wish there was a way I could go back and delete what I just said, but I cannot. Y can equal 0 because if x equals 0, y will equal 0. So we see from our graph that it is crossing the y-axis right here. So there are no horizontal asymptotes in this case. Okay, we're not going to do the quick review right now. We'll probably do that as a warm-up next class period, so that is it.